In the second installment of the lecture, we are going to talk about radioactivity and nuclear decay. So, what are nuclear reactions? Well, nuclear reactions are reactions that occur in the nuclear level. And when we talk about the nuclear level, you just have to remember we're talking about the nucleus. More specifically, the protons and neutrons, which are the subatomic particles in the nucleus. There will be three types of reactions dealing with nuclear reactions. The first type is nuclear decay. The second type is nuclear fission. And the final type is nuclear fusion. In nuclear fission, you have a larger unstable nuclei that is bombarded by some particle, such as a neutron or a proton, and it is broken down into smaller nuclei. For example, here is a stable uranium, and it is bombarded by a neutron, and now it's become unstable, and it breaks into smaller krypton and barium. Now, with nuclear fusion, you're actually combining two smaller nuclei to form one large, stable nucleus. In this image, you have deuterium, which is an isotope of hydrogen, and tritium, which is also another isotope of hydrogen. They both combine to form helium, and to make it stable, a neutron is ejected, and so you have two isotopes to form one larger element. But in this tutorial, we are going to focus on radioactive decay. Radioactive decay is a spontaneous disintegration of nucleus into a smaller nucleus, and particles or electromagnetic radiation are emitted. Now, disintegration just means breaking down. And as far as particles, you will learn they are alpha, beta, and a few more. And electromagnetic radiation is the energy photons that you were introduced to in the EMR spectrum. But in this case, we're going to talk about gamma radiation. So, just a brief overview. Radioactive, you have a large unstable atom, and it goes through decay, and it spits out particles, and you now have a new, lighter, more stable daughter product. So, alpha decay. An alpha decay occurs when you have too many protons in the nucleus. And so, when you have too many protons in the nucleus, you end up emitting an alpha particle. And an alpha particle is the same as the nucleus of a helium atom. So, you end up having 4, 2. So, here's helium. Helium atom. So let's take this example of polonium emitting an alpha particle and decaying to uranium-236. When polonium-240 breaks down and emits an alpha particle, it loses 2 protons and 2 neutrons. And so when it loses 2 protons and neutrons, it has a new atomic mass of 236, because now the molar atomic mass is 236, and it has a new atomic number, which is 92, because it lost 2 protons. And so if you look on the periodic table, it's uranium. And this is how we got this. How you know you got this particle right here, uranium-236. When you go through alpha decay, you typically have too many protons, and you emit an alpha particle, which is the helium nuclei, and it has 2 protons and 2 neutrons, and it gives you an atomic mass of 4. Now, when you are doing examples and you're trying to write a chemical equation for this, you start off, for example, with uranium-238, and it has an atomic number of 92, which means it has 92 protons, and if it goes through alpha decay, it loses 2 protons, and you end up with 90 protons. Since it has 90 protons, it's no longer going to be uranium. This is the reason why there is an arrow to indicate that there is a yielding process, and now you have thorium-90 But how did we get 234? It's because, remember, you lost 2 protons and 2 neutrons, so that's an atomic mass of 4. So 238 is the original atomic mass. We lost 4 particles, subatomic particles, and now you have a new mass of 234. In order to finish your chemical equation, you have to add that alpha particle in there. So let's go ahead and write our first chemical equation for the decay of astatine 209. Astatine 209, it has a atomic mass of 85. If it goes through alpha decay, it loses 2 protons, and so now my new atomic mass is 83. And I can go ahead and write what I'm losing. So I'm losing an alpha particle, and I now have a new atomic number, and I also have a new atomic mass because I lost 4 subatomic particles, and my new atomic mass is 205. So I'm going to go ahead and put 205 on the top. If I look at the periodic table, the element with the atomic number of 83 is bismuth. And so this is how you would write a chemical equation for an alpha decay of astatine 209. In a beta decay, you have too many neutrons in the nucleus, and a neutron converts into a proton and emits a beta particle. A beta particle is basically an electron with a -1 charge. To illustrate what is occurring, I'm going to use fluorine 20, and has atomic number of 9. If we look at number of protons and neutrons, it has 9 protons and it has 11 neutrons for a total of 20 for the atomic mass. When it goes through beta decay, we lose a neutron, and that becomes 10, and we gain a proton, and that becomes 10. Our atomic mass does not change. This is the reason why we have an atomic mass of 0, but our proton does change. We gain a proton, and there's a reason why we have a -1. So in this example, we have radon-228. This isotope has 88 protons, as the atomic number is 88, and it has 140 neutrons, and that gives it an atomic mass of 228. Now, if it goes through beta decay, we end up losing a neutron, and you end up with 139, and you gain a proton, and so that ends up as 89. Our atomic mass is still the same, 228. And so when we look at our product, 228, 89, actinium, and you end up ejecting a beta particle. In a beta decay, you have too many neutrons, and you eject a beta particle, which is an electron with a -1 charge. If we look at the example for iodine 131, you have 53 protons, and you have 78 neutrons. If you go through beta decay, you lose a neutron, but you gain a proton, and so your new numbers are 54 protons and 77 neutrons, but your atomic mass remains the same, 131. And so since we have a new atomic number, we should have a new element. So atomic number is 54, that's xenon, but it has the same atomic mass, and you have to write also the beta particle in your chemical equation. Here's your reactant, and here are your products. So let's go ahead and write our beta decay for carbon-14. Here is the standard nuclear notation for carbon-14, and if it goes through beta decay, I'm going to emit a beta particle. Okay. If I originally have 6 protons and 8 neutrons, when you go through beta decay, you lose a neutron and you gain a proton. So now my atomic number for my new product is going to be 7, but my atomic mass does not change. If you look on the periodic table, my new element that has atomic number of 7 is nitrogen. And this is the chemical equation you would write for the beta decay of carbon-14. You have a positron emission when you have too many protons in the nucleus. And in that case, you have a proton converted into a neutron, and a positron is emitted. A positron that is emitted is basically the mass of an electron, so it's an electron with a charge of proton, and there's a reason why it has a +1 charge. In my example here, I have carbon 11, and so here is my standard nuclear notation. So we have to look at the number of protons and neutrons again. So carbon 11 has 6 protons and 5 neutrons and an atomic mass of 11. If it goes through positron emission, I lose a proton, and so my new number of proton is 5, and I gain a neutron, and I have now 6, and my atomic number is still 11. So if I write this down, I emit a positron, so 0 plus 1 E, and then my new element, which has 11 as an atomic mass and 5 atomic number, and on the periodic table, atomic number 5 is boron. So the positron emission, just like in the example above, in the last slide, you had carbon 11, and when it went through positron emission, it lost a proton, so it changed to 5, but my atomic mass stayed the same, so my new element produced is boron 11. So let's go ahead and do cesium together. It has 55 protons and 82 neutrons, and when it goes through positron emission, it loses a proton, and so it's now 54 protons, and gains a neutrons, 83 neutrons. My atomic mass doesn't change, so I have 137, but now I have a new proton, and so my element is xenon 137. So in electron capture, you have too many protons, and what happens is if you have electrons in the orbitals, it gets absorbed into the nucleus and combines with one of the protons to form a neutron. So if we look at this example, let's take a look at beryllium-7. Beryllium-7 has 4 protons and 3 neutrons. When it captures an electron, the proton absorbs the electron and it turns into a neutron, so we lose a proton and it becomes 3, and we gain a neutron, so this becomes 4 neutrons, and our new atomic number is 3, but our atomic mass stays the same, and if you look on the periodic table, it is lithium-7. Where does the particle go? Actually, it goes on the reactant side rather than the product, because you require it in order to form your product. So let's look at a couple of electron capture examples. Let's take the first one, sodium-22. Actually has 11 protons, 11 neutrons, and if it captures an electron, we lose a proton, but we gain a neutron, and so we have a new element, neon-22. So let's go ahead and do the electron capture of potassium-40. Potassium-40, if it goes through electron capture, it loses a proton, and so it ends up with 18 protons, and you gain a neutron, so we now have 22 neutrons. So my new product is going to have the same atomic mass, but now has a new atomic number. And so I have argon as my new element. So gamma emissions are basically high energy electromagnetic waves that are a byproduct of all decay processes and is indicated by the symbol 00 gamma. And gamma it's sometimes considered as the upside down fish. And it's just high energy that's a byproduct. And you guys learned gamma is part of the electromagnetic spectrum. And so it's just in the higher energy range. So in summary, the particles that you should be seeing for alpha is the helium nuclei, and the particle mass is 4, the particle charge is 2, and so the change in your mass number should be decreasing by 4, and the change in atomic number is decreasing by 2. Beta emission is O minus 1, which is the an electron, charge -1. It has no mass, and it has a charge of -1. So your mass does not change, and your atomic mass, atomic number does change by increasing by 1. For positron emission, you have a positive electron, and it has a mass of 0 and a charge of 1. It doesn't change your the mass, and it decreases your atomic number by 1. Electron capture is the same thing as your electron, like in beta emission. It has no mass and a charge of -1. It does not change your mass, but this time, unlike beta emission, it decreases your atomic number by 1. And gamma emission is represented by gamma, and it has 0 mass, 0 charge, and it does not change your mass, and it does not change your atomic number. I hope this table helps summarize the particles. Here are some problems I'd like you to try on your own. Go ahead and take a pause. Once you unpause it, I will have the answers up. So make sure you try the problems first, and then I will have the answers up. Here are the answers to these problems. Now in your packet you may have more, so please work on the problems in your packet and come to class with any questions that you have. Thank you.